Okay, so today we're going to start rotational volume. Okay, we did cross-sectional volume, and this is very similar. The difference is that instead of using different shapes like squares, triangles, rectangles, semicircles, rotational volume uses two shapes. We either use a disc or a washer to find the volume. So today we're going to start with the easier of the two, which is a disc. Okay, so basic example would be something like this. Suppose I start with this two-dimensional curve, okay? Square root of x, something we know. And my boss wants to use this shape to build the nose cone of a rocket, okay? So what I'm going to do is I'm going to put a piece of wood into a lathe and turn it to match this curve. So basically it's those videos where you see the piece of wood spinning and you create a shape out of that. And that's what we're going to be doing here. We're going to use this two-dimensional shape to make this three-dimensional shape. And the way it's done is, if you think about it, if I take this two-dimensional shape, this y equals the square root of x, and start spinning it really fast, if you watch this piece right here, it's going to start going in a circle like this, really fast. Or if you track any of them, they're basically going to be spinning around this axis, and it's going to create this three-dimensional shape. Okay? And this is what we're talking about. This is rotational volume. And of course, when we talk about it, this is what a lathe looks like. And you can see in this picture, this guide arm right here follows this two-dimensional shape here and turns this square piece of wood, as this bottom part rotates this way, it actually cuts and matches it exactly. Okay, and so that these spindles are exactly the same shape. Or sometimes they'll do it freehand. Like that's a lot of, like if you go to YouTube, there's a lot of videos like that where it spins and they just carve it straight out of it. They do it with metal too, which is kind of cool. But this is what a lathe is. Okay, so basically, how can we find the volume of this cone? Well, just like we did when we started doing areas, we started by thinking about just one piece, one small piece. Okay? So in the two dimensions, it'll look like this rectangle. And that's where we started when we first did area. We did rectangular approximation method. Okay? But when you take this small little rectangle and you start rotating it, spinning it, it creates this three-dimensional piece right here. And you can see specifically that this distance right here, from here to here, ends up being basically the radius of this three-dimensional shape. Okay? And these little pieces are actually little slices, and they are cylinders. Okay? Because their base shape is a circle, and it has a little bit of height to it. So each one of these pieces is going to be a small little cylinder. Okay? Does that make sense? I hope so. Now, the volume of each one of those cylinders is going to be the circle, the equation of the circle, times its thickness. In this case, r is the y value of the function. Okay? Like I said, this part right here, this is the radius. It comes from this distance from here to here, which is the y value. Okay? Which means, basically, that our volume ends up being pi times r, which is the square root of x. Now notice, it's still, we can think about it as the function on top minus the function on the bottom. That distance still holds true. Okay? Because the function on the bottom is 0. So this thickness, though, is going to be what we need to think about. And in this case, the thickness is a small change in x. And when we deal with that in calculus, we talk about it being dx. Okay? So So basically this ends up being the volume of each one of these different cylinders, because there are going to be a ton of them that we're going to have to add up. I wish we had a function that adds up a bunch of stuff for us. Oh wait, we do. The integral. Remember, the integral came from originally, when we started this, how to add up all of those different little rectangles to find area. And in this case, it's now not adding up rectangles, it's adding up all of these little volumes to find the total volume. And at this point, it's just a definite integral. Now, this isn't any different than what we've been doing, and I'll show you when we get to the equations. Okay? So when we add up all of these, we evaluate the integral. So the square root of x squared is x. Add 1 to the power divided by the new power, plug in 4, and the volume is 8 pi. Super simple. Okay? Now, the hardest part of that was finding the equations. So this application of the method of slicing is called the disk method. The shape of the slice is a disk or a cylinder, so we use the formula for the area of a circle to find the volume of the shape. Now, if the shape is rotated around the x-axis, then the formula is pi r in terms of x squared dx. So this looks just like our cross-sectional volume. Our equation for our cross-sectional volume we used was a of x dx, because the area changed based on whichever shape we used. But whenever we do rotational volume, the shape we're going to be using will always be a circle. That's why we don't have an area. We're always going to use pi r squared for the area. And then, of course, dx gives me the height. Now, the radius equation, the length, just like before, the base and cross-sectional volume, the radius is function on top minus the function on the bottom. So as soon as you see anything about rotating about the x-axis, you know that that's the equation you use. If it says it's rotated around the y-axis, it's the same equation in terms of y, and then our radius is the function on the right minus the function on the left. So as far as equations, it's identical to our cross-sectional volume. Right? Wow. All right, so let's look at your y values in first and get x values. Okay. Now, drawing it is going to be the most difficult part when we start doing these rotational volumes. So once we have our graph, let me show you how you're going to want to figure out what the 3D looks like. So the first thing you're supposed to do is, since it's revolved around the y-axis, I tell my students, draw your little arrow. So it's going to be revolved around here. Then whatever line is your revolution, you are going to basically reflect over that line. So I'm going to draw the same piece reflected over the y-axis. Okay? Then all you're going to do now is just like you did in middle school when you drew those S's, where you draw the 3 marks and 3 marks and you diagonally connect it to make it look 3D. That's kind of what we're going to do here. We're just going to draw ellipses like this to make it kind of look 3D. So if I follow this point right here and it starts rotating around, it's going to look like that. If I follow this point right here and start rotating around, it looks like this. Pick any point, and basically it's going to start going around and around like that, and it gives you kind of your 3D shape. That is the easiest way to kind of get an idea of what your shape is going to look like. And you can see it kind of pops out at that point. Okay? That's the easiest way to draw these. So, here's our shape. Then we're going to know which equation we're going to use. We're using horizontal. So the thickness is dy. The radius is the x value of the function, this distance right here. We plug it into our equation, simplify, integrate. The integration, or the antiderivative of 1 over y, is the natural log. Then we plug in top minus the bottom. use our natural log properties. The natural log of 1 is 0. And then I can simplify. 4 is 2 squared. Using the log property, I get 2 pi times the natural log of 2. Okay? So the hardest part about this is knowing which direction you're going. But also thinking about when we did this, the radius, it's the right function minus the left. It's still that. But of course, this is x equals 0. That's the y-axis. So it's the right function 1 over square root of y minus 0. And that's it. That's rotational volume. Not a very hard concept, but you got to know how to set up